Hey guys, welcome back. So this week is going to be a little bit different. This is kind of a learning curve for all of us. So instead of doing or putting up the PowerPoints on Google Classroom, I decided it would probably be easier if I created a video going through each of the concepts and lessons that we do. What I'll go ahead and do is print off the slides and I'll kind of put them up here on my whiteboard, and I'll go through each of the concepts with you, and then I'll kind of make some drawings and diagrams that will help you grasp onto things a little bit better if you're a visual learner. And then I'll kind of go into more depth with the concepts. So to start off this week, we're going to go ahead and do a review of last week's lesson very quickly, which was over atomic structure. So we'll go over the basics of that. So again, here is the structure of an atom. It's a pretty simple drawing. Within the nucleus, which is our center part here, we have neutrons and protons. Remember, our neutrons, which are represented by our little blue dots here, they have a neutral charge, and then we have protons, and the protons have a positive charge. Now, what surrounds that nucleus, remember, is the electron cloud, and your electrons are going to have a negative charge. So just a really quick recap of what we went over mainly last week. All right, guys, so this week we are going to be going over the masses of atoms. So before we get into what kind of makes up the mass of an atom, we're going to go on a bit of a smaller level and look up what makes the mass of our particles, like our protons and our neutrons. So I do have your slides over here. I know it may be kind of hard to see, but you are able to go back onto Classroom and kind of look through these slides if you want to reread them and kind of look at them yourself. But I'll have these up here just for reference so I can go through them easier with you. So starting on a smaller level, there are smaller particles of matter called quarks to exist, but scientists still consider atoms the basic building blocks of matter. So what we're going to go ahead and look at are quarks. So what are they? They are smaller particles that make up our protons and our neutrons. And you can see on the table on your slideshow that there are 6 main quarks to exist. We're going to go over the up quarks and the down quarks first, and then I'll kind of get into the other ones. So the idea of quarks originated around 1964. Two physicists named Murray Gell-Mann and George Zweig suggested that known particles that make up an atom, so our protons and our neutrons, could be explained as being combinations of 3 smaller fundamental particles. And you'll see here I've got your protons and your neutrons drawn out, and we have those 3 smaller fundamental particles, or as we know them, quarks, that make those up. So I'll kind of get into what those are. So quarks, they were needed to have a fractional charge in order to work. So quarks, depending on what they are, they have different masses, different charges, and different spins. So our up and our down quarks are our most common because they make up our protons and neutrons, which we are most familiar with. So the charge of an up quark is represented in a fraction, as it is with a down quark. So the up quark has a positive 2/3 charge, while the down quarks have a negative 1/3 charge. So let's go ahead and take a look at what quarks make up the proton. So within our proton, again, we have 3 quarks that make it up. We have 2 up quarks and 1 down quark. So remember that protons have a positive charge And we get that by adding up all of the charges of the quarks that make up the proton. So if we have 2 up quarks, we'll have 2/3 and 2/3, and then we will have a negative 1/3. When you add all of that up, that will equal 3/3 or 1, so it has a +1 charge. Now, if we look at our neutrons, again, we have 3 quarks that make it up, but instead of having 2 up quarks and a down quark, we have 2 down quarks and an up quark. So when we add all of the charges of these together, we have a negative 1/3 charge, another negative 1/3 charge, and then a positive 2/3 charge. That will equal out to be 0, so it will have no charge at all. Now, like I said, there are 4 other quarks that go along with our up and our down quarks. These are called strange quarks, charm quarks, and then top and bottom quarks. So, like I said, we won't be looking into those other quarks as much, just mainly these 2, as they make up our protons and our neutrons. But the strange quark, it got its name as it was observed in particle decays that lasted, or they had a longer lifetime than they were originally supposed to. Charm quarks, nothing really sciencey about it. I mean, there is, but we won't really get into it here. But they were called charm quarks because of the way they fascinated physicists at the time. And then our top and our bottom quarks are just pretty much the logical counterparts for up and down quarks. So that's mainly everything that we are going to get into when it comes to quarks. So now that we've got kind of a picture of what goes on within the protons and neutrons, we can move on to atomic mass, which is going to be very important when we are navigating our periodic table. So atomic mass is composed mostly of protons and neutrons in the nucleus, and it is also called our mass number. And we will be looking at atomic mass and mass number coming up, what it looks like on the periodic table within each of the elements. Okay, so now we are going to be moving on to atomic number. Like I said, this is going to be very important when it comes to navigating our periodic table. So I've got an example for us up here. We're going to go ahead and look at the different parts of each element's component and what they look like on the periodic table. So I just picked an easy one, carbon. So we're going to look at what each of these numbers means. So as we learned last week, remember that each of our elements has a symbol. For example, on carbon, it is going to be a capital C. Remember that even if they have 2 letters, only the first letter is going to be capitalized, okay? So what our atomic number is, and let me go ahead and hang your slide up really quick. Your atomic number is the number of protons in an atom. It is also the number of protons that identifies the element. So carbon is identified by its atomic number, which is 6. And we'll see that up in the top left-hand corner with pretty much like all of your elements on the periodic table. So right here is going to be your atomic number up in the top left-hand corner. Down here at the very bottom is going to be your mass number. So this is going to be very important when we are looking at finding the number of neutrons within the nucleus. So we know that carbon obviously has 6 protons in the nucleus because your atomic number is the number of protons in your atom. So if we wanted to find our number of neutrons within the carbon element, what we would have to do is take our mass number and subtract our atomic number. So our mass number for carbon is 12.001, but we'll go ahead and just round it up to 12, or round it down to 12. So we have our mass number here, which is 12, and then we are going to subtract our atomic number, which is 6, okay? So again, it's because we have 6 protons. Now, then we have 12 minus 6, which is 6, so that means we're going to have 6 neutrons within the carbon element. Now, just a heads up on this, guys. Carbon is one of the elements where it has the same number of protons as it does neutrons. And it is not like that for every element. So don't think that just because this one is like that, that all of them are going to be like that. So again, you'll always want to remember this formula if you want to find your number of neutrons within your element. Okay, so the next thing that we are going to talk about in this lesson are isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. And we have one example up here. I believe that it gives you a different example in your slideshow, but yeah, they do. They give you boron. But we're going to talk about the isotope hydrogen. But before we do that, let's go ahead and remember some background information that will help us with understanding isotopes. So remember that an element is usually defined by the number of protons in its nucleus. And remember that it's its atomic number that you see up in the top left-hand corner. So for example, carbon is defined by the 6 protons that are in its nucleus. So if the number of protons in the element change, then the element itself will change. Okay, so if it goes from having 6 protons to 7 protons, obviously it's going to change into a different element. So the number of protons is equal to the number of electrons in an atom. So if there is 1 proton in an atom, then there is only going to be 1 electron in its electron cloud. If there are 3 protons within an atom, then there's going to be 3 electrons in its electron cloud, and so on and so forth. But remember, like I said, not always do we have the same amount of protons as we do neutrons. So the number of neutrons in an atom can change between the different numbers of the same element. So you can keep adding neutrons to the same amount of protons and it will stay the same element. So we have an example here, and these are different isotopes within the element hydrogen. So first of all, we just have hydrogen, which we're very familiar with. Hydrogen is number 1 on the periodic table because it only has 1 proton. Okay, so it has 1 proton in the middle, and it has 1 proton floating around one electron floating around its electron cloud, and that does not change. Remember, what does change is the number of neutrons. So these are some different types of isotopes within the element hydrogen. So here we have deuterium, where we have 1 proton and 1 neutron, okay? And then we have tritium, which is where we have 2 neutrons and 1 proton. And hydrogen isn't the only element with isotopes. For example, we have over here, it shows you in your slide, boron 10 or boron 11. So these different isotopes can have different properties. Okay, so moving on with that, we can go ahead and start to take a look at average atomic mass. Now, average atomic mass is the weighted average mass of an element's isotope. Okay, so the last thing that we are going to look at today is some examples of common mass numbers. I've scooted it in a bit closer so that you can see these better. So this, again, it's on your slideshow. It's basically just a chart of some common elements, their symbols, their atomic numbers, the amount of protons that they have, the amount of neutrons, their mass numbers, and their average atomic mass. And you'll see that is labeled as AMU, this is just your average, your atomic mass unit. So the first one that we have up here is boron. Its symbol is B, and its atomic number is 5. So that is the number that we would see up in the top left-hand corner. Again, your atomic numbers and your protons are always going to be the same. So boron's proton number is going to be 5. The amount of neutrons that boron has is 6, and then its atomic mass number is 11. So if we did not know the amount of neutrons that boron had, remember we could use that formula that we talked about where we take the mass number and subtract the atomic number. So if we were to take 11 and subtract 5, we would get 6 neutrons, okay? And then the average atomic mass of boron, which is its mass altogether, is 10.81 AMU. And this kind of goes on, and I'll explain all of these. So if you want to stop the video now, you can, but if you want to learn some more information about what each of these is, you can go ahead and keep watching. So carbon, again, we went over this. Its atomic symbol is C, capital C. Its atomic number is 6, and the amount of protons that it has is 6. The amount of neutrons is also 6, and we can figure that out by taking its mass number of 12 and subtracting the atomic number of 6. Its average atomic mass is around 12.01. Okay, then we have oxygen. Its symbol is a capital O. Its atomic number is 8, so its protons are 8. And then, kind of like carbon, it also has the same amount of neutrons. Okay, so if we were to take our mass number of 16, which remember is at the bottom of the little square, and subtract our atomic number, we would be getting 8 neutrons. And if you recognize a pattern, you'll see that the average atomic mass is around the same as its mass number. Okay, so there's not a lot of difference between these. Again, it's just kind of how they rounded it. So the average atomic mass here is 16 AMU. Then we have sodium, which has a symbol Na. Remember that only the first letter is capitalized whenever we have 2 letters symbolizing an element. So here is Na. Its atomic number is 11, so its protons are 11. It has 12 neutrons, so if you were to take its atomic mass number, 23, and subtract 11, you would get 12 neutrons. And sodium's atomic mass is around 23, technically 22.99. And lastly, we have copper, which is represented as a symbol capital Cu. Its atomic number is 29. It has 29 protons. This has actually 34 neutrons, and then its mass number is 63. So you take 63, you subtract 29, you would get 34 neutrons. And then obviously here its atomic mass, or average atomic mass, is 63.55 AMU. So that's going to go ahead and wrap up our lesson for today. If you guys had any questions over this, please feel free to comment or email me. Hopefully this was a little bit clearer for you to understand rather than just like going through the slides on your own. You get a little bit of background information. All right, guys, thank you. Hey guys, welcome.